Hi everybody, I'm Giulia Corniani and I'm a PhD student at the Active Touch Laboratory of the University of Sheffield. Today I present this work about strains in the skin subsurface investigated using optical coherence tomography. The skin is our largest sensory organ and it is responsible for the sense of touch. Indeed, every tactile interaction is mediated by the external layer of the skin, which receives the stimulus as a mechanical deformation and propagates it through the skin surface and in depth. In deep layers of the skin, the mechanoreceptors transform the mechanical stimulation into spike trains, which encode the stimulus information. My focus in this work is at the very early stage of this process, as I am studying how the mechanical stimulation happening at the skin surface propagates in deep layers and finally reaches the mechanoreceptors. To look at the sublayers of the skin, I'm using images acquired with optical coherence tomography, which is a completely non-invasive imaging technique. With this technique, we can image the whole stratum corneum, the viable epidermis, and down to the dermis-epidermis junction, which is where the type 1 receptors sit. In my study, in particular, we acquire images with a rate of 20 frames per second, and we reconstruct videos like this. We slide against the finger transparent plastic surfaces with different shapes, both embossed or engraved. So basically, while the fingertip is stuck on a finger holder, the plate slides against it. The transparent surfaces are mounted on a holder which is fixed on a linear stage that moves back and forth. In the case study that I'm presenting today, the surface has a round dot embossed and slides against the finger with a 2 Newton load and a speed of 2 millimeters per second. After the images acquisition, the first step is to process the images to remove noise and artifacts and to stabilize the motion. Then I track some features corresponding to the top of each ridge and the valley between two consecutive ridges. I track these features at the skin surface, at the border between the stratum corneum and the viable epidermis, and at the dermis-epidermis junction. With the tracked features, I build in every frame some triangles. Every triangle corresponds to a single ridge in the stratum corneum or in the viable epidermis. These triangles are then used to calculate the strains with the Green-Lagrange strain equations. Basically, I look at the displacement of each triangle from frame to frame, and I compute the strains in the direction parallel and normal to the movement, and also the shear strain. Before looking at the result in detail, just a couple of remarks. The thin green lines are the strains for each triangle in each one of the transits of the round dot, while the thick black line is the average over all the triangles and all the dot transits. The strains were aligned, and the strain at zero distance is the strain measured when the center of the dot is precisely above the top of the triangle. Looking now at the strains in the stratum corneum, first of all, there's a good symmetry around the 0 point. In the horizontal direction, triangles get stretched when the dot is approaching and subsequently compressed when the dot is going away. In the vertical direction, the trend is the opposite, as triangles first get compressed and then stretched. The shear strains on the overall is lower in value and it is just compressive. If we now compare the strain measure in the stratum corneum and the strain measure in the viable epidermis, the trend is generally the same in both layers. But it's worth noticing that the strain in the viable epidermis, in particular the vertical strain, seems to be higher in value, and this might suggest a magnification of the strains in deeper layer, so closer to the mechanoreceptor location. In conclusion, with this initial analysis, we assess the viability of using optical coherence tomography to investigate the mechanical properties of the subcutaneous tissues. Also, our initial findings suggest that there might be a magnification of the strains in deep layers. For sure, we will expand this analysis to accurately verify this initial result. Soon, we will also explore how the stimulus features, as for example, the speed of the plate, or the load, or the plate geometry, affect the strain in the skin. We also want to use our data to compare with existing theoretical models of the skin mechanics. In conclusion, let me thank all my collaborators whose contribution has been and will be fundamental to this project, as well as New Touch, the Marie Curie Innovative Training Network, which is supporting my work. If you have any questions, do not hesitate to drop me an email or to show up in the live session of Thursday morning. Thank you for watching my presentation and enjoy the rest of the conference.